Hey guys, Miss Marusik here, and in this video, we're going to talk about writing electron configurations in orbital diagrams for elements on the periodic table. We're going to be showing an address for all of the electrons in that particular element. Now, as a reminder, in our previous video, we discussed the pieces to the address: the energy level, the sublevel, the orbital, and the spin, the 4 quantum numbers. Orbital diagrams actually show all 4 of those quantum numbers. So you'll see the S, P, D, and F, you'll see the boxes, you'll see the arrows, you're going to see the whole thing. But sometimes those can get really overwhelming to start with because there's a lot of information on those. So we're actually going to start with writing what is called an electron configuration. It's kind of an abbreviated address. It shows some of the information, but not quite all. You notice it's going to show us the energy level, the sublevel, and the number of electrons in that sublevel. I think it's often helpful to start with an electron configuration, and then if necessary, then you can continue on and construct an orbital diagram for it. Now, there are some other blanks on this page. We're going to come back to those blanks here in a little bit. What I'd like to go ahead and do is look at the blank periodic table that's on the top of your next page. Now, I showed you in the previous video how the sections on this periodic table tie to where certain sublevels, our S, P, D, and F, fill up. And so it's going to be really helpful for us to label this periodic table kind of as we start to get going here, just so we can have an idea of what's filling up where. So as a reminder, in these first 2 columns, we're going to get S to fill up. And so sometimes this section is referred to as the S block on the periodic table. When we start with the S block, remember the first energy level does include S. So 1 S would fill up starting here. Now, this first row is kind of weird because 1 S is also fills up over here. So 1S kind of includes both of those boxes. But from here on down, we can just continue on with that counting. So the second energy level, 2S, would fill up here, then 3S across, then 4S across. But you notice I'm stopping at the end of that section there. 5S, 6S, and then eventually 7S. So again, this is our S block, and we start filling up the S sublevel at the first energy level number 1. All right, so next, let's talk about where P fills up. P fills up in this section over here. Now, we don't see P start until the second energy level. So I'm going to label this with 2P. And I'm going to make it go across. And then I'm going to continue with my count. 3P across, 4P, 5P, 6P, and 7P. All right. Next, our D block. D fills up in the transition metal section, so here in the central part of our periodic table. However, do you remember the first energy level where we see D? We see D start in the third energy level. So right here, this is going to be 3D filling up across. Okay. Now, I know some of you can say, ooh, 4S and then 4P, but this is 3D. I know. It looks a little weird, but I promise that is the correct order here. So then we're going to go 4D, then 5D, and then 6D. Now, as a reminder, Our F block is our lanthanide and actinide series. Now, what's interesting is that on some periodic tables, they will actually put this block into the periodic table and shift these sections all the way across, so that way we can have it fit in exactly where it's supposed to go. However, most of our modern periodic tables do pull it down to the bottom here, only because it's kind of saves some space if you're trying to print the periodic table on a single page. If you were to actually put these two rows where they go, you would end up creating this really long periodic table. By the way, if you want to see one, I actually have a poster of one in my room, so feel free to stop by if you want to see one of those in action. Do you remember what energy level we first see F fill up in? That's right, we see it in the 4th energy level. So 4F and 5F. Now I'm going to tell you a trick. What I have a lot of people do is they remember, hey, this is S, P, D, and F. And then they remember that it goes in order of 1, 2, 3, 4. So 1S, 2P, 3D, 4F. And they'll just, if they see a periodic table, kind of write down where each of those sections start at. And so then they can kind of continue on from there. Now, you're thinking, okay, great, I've got this all written out. How in the world do I use this, okay? So let's talk about this process for a particular element. So I'm going to come down here to the bottom of this page, and notice on this example, it wants us to write the electron configuration for cobalt. So we're going to start off there with our electron configuration only. Now, here's 2 important things I have to be able to do. Number 1, I need to know what element cobalt is. So this is where you have to know your element symbols. So this would be CO. And next, I would want to go figure out where it is on the periodic table, what its atomic number is. And so I would pull out my periodic table, and I would go find cobalt, and I see it's here, it's number 27. And so what we want to do is we want to write everything we went through in order to get to cobalt. We are going to be showing the address here for 27 total electrons, because that's my atomic number, okay? So kind of scooching back up here for a second. Let's see here. I'm going to go ahead and show cobalt on here. You don't have to, but I'm going to go ahead and kind of write it in here. Cobalt is right there. And I'm going to read this table like a big old paragraph. I'm going to read everything I went through from start to finish. So I can see here that first I'm starting off at the 1st energy level with an S sublevel. I'm starting off at 1S. And I also want to include how many electrons would be in that particular sublevel. Well, there's 2 of those blocks I'm going through that have 1S. So what I'm going to do is I'm going to come down here and I'm going to write 1S with a 2 as an exponent. That is to show in the 1st energy level, in the S sublevel, there are 2 electrons there. So then I'm going to continue on. Well, now the 1st energy level is full. Remember, the 1st energy level can only hold 2 electrons. So anything else now would go into the 2nd energy level. So the next thing I go through after 1S is I go through 2S. And look how many blocks of that we're going through. We're going through 1, 2 of those. So I'm going to come down here and I'm going to put 2S with an exponent of 2 to show in the 2nd energy level, we have our S sublevel with 2 electrons. Now, that's not everything that the 2nd energy level can hold, because remember, it can hold a grand total of 8. So let's think about where those other 6 electrons would be. Well, those other 6 electrons would be here in 2p. And I notice in 2p, that's 1, 2, 3, 4, 5, 6 electrons across, or 6 blocks across to represent the 6 electrons. So I'm going to come down here and put 2p, 6. Okay, so now I'm going to come back up here, and after 2p, I'm going to continue reading this like a paragraph. I'm going to write 3s down, and I see I went through 2 blocks of that. And then I'm going to continue on, again, reading this like a paragraph. So after 3s, I come across here to 3p, and again, this is going to be 6 across. Now 3p, 6. Now, I know a lot of you remember that the third energy level can hold a grand total of 18 electrons, but our filling order does something a little bit weird here. What happens is that there is so much energy associated with those D clover shapes that it ends up with a higher energy amount than our 4s electrons. So there's a little bit of quirkiness to the filling order here. But that's okay, because here's the good news. If I follow my periodic table pattern here, I will catch that quirkiness of the filling order here. So I'm going to come here, and next I see 4s. Okay, so I'm going to have 4s, and I'm going to put an exponent of 2. And then I'm going to go to this 3D. Now I have to be careful because I didn't fill all the way across this 3D. So I want to count how many I went through, including the block that has CO. So that's going to be 1, 2, 3, 4, 5, 6, 7. So I'm going to only have 3D filled with 7 electrons. It's not going to be filled all the way to 10 electrons. Now, if we did this right, we should see a grand total of 27 electrons being represented. So let's see if we have that. 2 electrons in the first energy level in the S sublevel, so there's 2, plus another 2, so that's 4, up to 6, that's going to be 10. Another 2 would get me to 12. Another 6 would get me to 18. Another 2 would get me to 20, plus 7 more would be 27 electrons. And so there's my grand total there that I was looking for. As a reminder of what each of these parts are showing, the big numbers that we see in front, like the 3 and the 4 here, these are representing the energy level. The S and the D's and the P's, those are representing the sublevel. And then these exponents here are representing the number of electrons in that particular area. So you can see it shows some of the information, but we did not show specifically what orbital we're in, nor did we show the spin of those electrons. And so that's where we can kind of continue on with this and show some more information. Now, before we do that, I actually want to go back for just a minute to the page we looked at previously. There are some rules that we need to talk about before we fill in an orbital diagram. And that is this section here that says rules for arranging electrons. When we're doing the orbital diagrams with the boxes and the arrows, there's some guidelines that we have to make sure that we follow as we're filling in stuff. The first is what is called the off-bow principle. This states that electrons are placed in orbitals of lowest energy amount first. You remember how we wrote down 4s before we wrote down 3d? That is because even though it's in a higher energy level number, 4s electrons actually have less energy amount than 3D electrons do. And that's because of the weirdness of the shapes of those D electrons. So a little bit of quirky nature to that there. So we have to be really careful because that energy amount is determined not only by energy level, but also by the shape. So the filling order tells us the correct order to write these in, that our lowest energy amount ones would always fill up first. The higher energy amount would fill up later. Our next rule is what is called the Pauli exclusion principle. And we talked about this without saying the name of this law in our previous video. We said that an orbital can only hold 2 electrons, that each one of those crazy spaces only has a max of 2 electrons it can hold. And so that makes it exclusive to those 2 electrons. Also, because the 2 electrons in that space would have to have opposite spins, that prevents any 2 electrons from having the same 4 quantum numbers. And we did discuss that a little bit, that each individual electron is going to have its own precise address. Okay. The third rule is something called Hund's rule. This states that when filling a sublevel, which contains orbitals of equal energy, so like if you're filling the p's up, like let's say you're filling up 2p and there's 3 of those orbitals there, that only one electron can enter each orbital with the same spin until each hold 1, and then they can double up. This has to do with electrons repelling each other. Obviously, Aufbau says we have to fill up orbitals of lowest energy amount first, but if you have those orbitals that have equal energy, the electrons are rather spread out than pair up if they can. And so we can put 1 into each before we are forced to double them up, and that will help prevent some of the repulsions that exist with those electrons. So now that we've kind of looked at those guidelines, let's go back now and talk about how to take this electron configuration into an orbital diagram. Now up here they've given us a skeleton model of an orbital diagram so we can kind of see what we're working with here. Now, what they've done is they've ranked this in order of energy, and really we should specify that this is an energy amount. And so they've showed us here that 1s electrons would have the lowest energy amount, and as we go up, you can see that energy amount increase. Now, they've put this kind of up and down to show us those energy amounts. Typically, to save space, we kind of write this side to side. So this is going to be the only one where we're going to show it kind of up and down here. But it is going to give us a good idea of how to fill this in. So first off, let's look at our electron configuration here. Remember, these exponents are telling us how many electrons we want to place. So in the first energy level, in our S sublevel, we're going to have 2 electrons. First arrow goes up, second arrow goes down. Those are our 2 electrons. They're going to have opposite spins because they're going to repel each other. And we've got to make sure that we're meeting the Pauli exclusion principle, that these need to have a different address, and that arrow provides the different address. All right, in the 2s, we're going to have, again, 2 arrows here. Now, 2p, we're going to have 6 arrows, but you remember how p had 3 different orientations? So we drew 3 different boxes for it. So this is where I'm going to put in those 6 electrons into those 3 different boxes, into those 3 different hourglass shapes. Now, this is where I need to start utilizing the Hund's rule that says I put 1 into each before I double up. So the proper way to fill this is 1 into each of these, and then I come back and double up. Now, I'll be honest, here, since you're filling up all 6, did it really matter how you filled it? No, but it's good to get in the habit, and so that way, when we get to our last one, we fill it up correctly. All right, so next, 3s. According to our electron configuration, we should have 2 electrons. 3p, according to our electron configuration, we should have 6 electrons there. So again, Hund's rule says we put 1 into each, and then we double up. All right, next, 4s. And you're thinking, oh, why are we doing 4s before 3d? Well, if you look, 4s is at a slightly lower energy amount than 3d. 3d actually has a little more energy to it because of the weirdness of the shapes. So again, we are following that Aufbau principle that says we fill orbitals of lowest energy amount first. So we're going to put those 2 electrons into 4s. And then last but not least here, we're going to fill up 3d. Now here's where we have to be really careful with Hund's rule. We have to put 1 into each of these. 1, 2, 3, 4, 5, before I can come back and draw number 6 and number 7. Now, if we did this right, remember, we should be showing 27 total electrons, and so that should mean that you drew 27 arrows in your orbital diagram. So just to clarify what we've done here, down here, when we wrote this right here, we were writing an electron configuration, which I usually abbreviate electron config, okay? Up here, what we were doing is constructing what is called an orbital diagram. you can see that the orbital diagram shows a little bit more information than we saw down here. This time, we again have our energy level. We again have our sublevel, just like we saw in the electron config, but now we also have the box. The box represents the specific orbital. And then finally, the arrow itself represents the spin. So all four quantum numbers are now represented. But you can see the orbital diagram's a little more involved than the electron configuration, but it does show more information, and so it takes a little bit longer to do. So quite often we will just write electron configurations for things. We don't have to write out an orbital diagram unless specified. And usually we'll try to keep the orbital diagrams a little reasonable. Like we won't ask you to do this for element 118, so you don't have to draw 118 arrows. So don't panic too much. We usually try to keep them, again, reasonable for you to be able to construct. Now, there are some additional questions down here that we want to address, okay? And to do that, I actually want to go back and look at the last couple things that were on the previous page. Talked about the valence versus the highest energy electrons. First off, the valence electrons, I know a lot of y'all are familiar with. Those are your outermost electrons, things that are not core. They're on the outside. They're the ones that we would involve when we're doing any kind of bonding. You lose and gain or share those electrons if you're doing ionic and covalent bonding. These are always the electrons that are the highest energy level, or N. Okay, so we look at those energy levels, see which one's the largest, and then we know that's where our valence electrons are at. Sometimes, though, it can be more than one. We got to be careful there. Also, our highest energy amount electrons are in the last sublevel that was filling, whatever the last thing you wrote was. Because remember, Aufbau says we fill lowest energy amount first, and so therefore the highest energy amount would come last. So we have to be careful. Sometimes the valence and the highest energy electrons are the same, but sometimes they're different. It depends on what kind of substance or what kind of element you have and what kind of energy levels and sublevels are involved. So we have to be really careful with this and asking us, hey, what do we have going on here? So with that said, let's look at our example that we saw. The first question to ask are, what are the highest energy amount electrons in cobalt? So as a reminder, highest energy amount are the last written. According to Aufbau, whatever the last thing you wrote was, that's going to be the highest energy amount. Well, what was the last thing we wrote? Well, last thing we wrote is 3d7. Those are your highest energy amount. They possess more energy than any of the other electrons in that particular element. However, remember, d electrons can't be valence. So look at our next question. It says, what are the outermost or valence electrons in cobalt? Well, if I look here, I look at those energy levels, 1, 2, 2, 3, 3, 4, 3. 4 was the highest energy level number that we saw. So the highest N, the highest energy level number, that's going to be your valence. Here, those are the 4s2s. So it asks, how many valence electrons does cobalt have? Well, cobalt will have 2 valence electrons. Those are on the outermost that would be involved in any kind of bonding. It then asks, how many core electrons do we have? Core electrons are anything that's not valence, that are in lower energy level numbers. And so here, if I have 27 total electrons and only 2 are valence, that means the other 25 would be considered core electrons. All right. Now, I know some of you are thinking, I don't know if I'm 100% with this yet. Don't worry. I wouldn't expect you to be. We're going to do a lot more examples with this in our next class, so don't panic, Okay. I always joke about electron configurations. They're like riding a bike. At first, it's really challenging, and you're like, I have no idea what I'm doing. I'm really lost. I'm going to fall. Yikes. What is happening? And by the end of it, it's smooth sailing. So we just needed to get to the point where it's smooth sailing. So don't panic yet. I promise you're all going to get there. If you have any questions or need any help, please feel free to email me. Bye, guys.